Okay, welcome back. This is our second example that we are going to be going through for impact. Now this time, this is example 15.11, and as you can see from the picture here, these disks are coming at each other at a particular angle off of the line of impact. So hopefully you can recognize this now as an oblique impact problem. And what we need to figure out are what are the x and y components of velocity of each disk after impact. So the masses are shown there. So for the mass of A is 1 kilogram, the mass of B is 2 kilograms, and we have a coefficient of restitution between the two disks of 0.75. Now you can see that VA is approaching the line of impact at a velocity of 3 meters per second at an angle of 30 degrees, and disk B is approaching the line of impact at 1 meter per second at an angle of 45 degrees. So in order to use our conservation of linear momentum and coefficient of restitution, we need to break these into x and y components. So we need to break our velocities into x and y, and we know that conservation of linear momentum is conserved, so momentum is conserved along the line of impact for the system of particles A and B, and the momentum is conserved individually for each disk alone along the plane of contact, which is along the y. So the first thing we're going to want to do is we're going to want to break up these velocities into x and y. So as you can see here, I am showing each one of these. VAX is 3 cosine of 30, which is 2.598 meters per second. Then we have the x component of VB1, so this is the initial velocity along the x direction. It's a minus direction, minus cosine of 45, which is minus 0.707, and then we can do the same thing with our y direction. So just verify that, for yourself. Make sure you understand how we're breaking up the components. And the next thing we're going to do is we are going to set up our conservation of linear momentum equation. Okay, so what I'm showing here is our conservation of linear momentum equation, and we have each of our particles initial. So we have our initial momentum of mass times the initial velocity, and again, we're only doing this along the line of impact, which is along the x-axis. So we're going to use our components in the x-axis for our velocities. So we have our initial momentum for B and A times their masses, respectively, and then we have our mass times our unknown final velocities in the x direction, A2 and B2. So we can get this equation, this is our first equation, VA2x plus 2VB2x is equal to 1.184. So here's our coefficient of restitution equation, VB2 in the x direction minus VA2 in the x direction, those are the unknowns that we need to solve for, divided by VA1 in the x direction minus VB1 in the x direction. And those we knew, we broke those up into the components, so we just plug in the values that we know. We know our coefficient of restitution is 0.75, so we can get an equation now with VB2x and VA2x, and this becomes our second equation that we can use. So in simplifying this ratio, we get this equation, VB2x minus VA2x equals 2.482, and this becomes our second equation. So now we have our first equation right here from our conservation of linear momentum, and we have our second equation using our coefficient of restitution. So we have two equations and two unknowns, and we can solve for our VB2x and VA2x. So in solving these two equations, we solve for VA2x, so this is our final velocity for disk 2 in the x direction, of minus 1.26 meters per second. Therefore, we know it's going to the left. And VB2x, we get a positive 1.22 meters per second, so we know it's going to the right. Now, the question asked for components in the x and the y. So we're going to use the conservation of linear momentum individually to each disk in the y direction, because if you recall from the lecture, along the plane of contact, which is the y direction, perpendicular to the line of impact, individually each disk will be conserved. So the momentum will be conserved because there's no forces that are acting along the y direction. There are no impulsive forces acting along the y. So we don't treat them as a system, we treat them as individual disks. So if we apply the conservation of momentum, the masses cancel out, and we just say that our initial velocity in the y direction must equal the final velocity in the y direction. So we just can say that VA1y equals VA2y, which is 1.5 meters per second, and it's positive, so it's going upwards. And VB1y equals VB2y, and that's negative, so it's going in the downward direction. So that completes this example. Now, if the question asked what's the total velocity for A and the total velocity for B, then you would use Pythagorean theorem to find the total velocity, which is the square root of the sum of the squares of each of the components x and y. And then you could use tangent of theta to solve for the angle, so the directed angle after impact. Okay, so just look carefully at the question. If it's looking just for the components, then you're done with what we did right here. If it asks for find the velocity and the direction of each, then you would need to take it another step and use Pythagorean theorem to solve for the total velocities, and then use tangent of theta to solve for the theta using y over x in that case.